Hi, it's Paul Anderson. I'm sure you're familiar with global warming, how increases in the amount of carbon dioxide is warming the planet, but you may not be familiar with global warming's evil twin, ocean acidification. The cause is the same, increases in the amount of carbon dioxide, but the mechanism is different. Let me show you a demonstration. This is regular distilled water, and I'm going to use a pH meter to measure the pH of regular H2O, and it's going to be right around 7. Now I'm going to take that same distilled water, we're going to put it in a bottle, and we're going to add carbon dioxide to it. We're using a soda stream machine to shoot carbon dioxide in it. It's now just carbonated water. We're going to put it in a glass, and we're going to measure the pH now. I want you to make a prediction of what you think the pH might be. You could even use your finger and point on the screen to where the pH scale is going to be. Let's see how you did. The pH is going to be 3.6. It's really acidic. Let me show you what's going on. So if we take carbon dioxide and water and mix them together, we get carbonic acid. Now that can quickly dissociate and form bicarbonate. What we're doing here is we're losing one of these hydrogen ions, and that can dissociate again and we can form carbonate. We're losing 2 of these hydrogen ions. Now, if we look at the definition for what pH is, pH, remember, is the negative log of the hydrogen ion concentration. What does that mean? The more of this H plus that we have in solution, the lower the pH is going to be, and it's going to be more acidic. If we add more carbon dioxide, more of it's going to move in, and we're going to have more of this hydrogen ion, and we're going to have a lower pH. Now, the levels of each of these can change. Each of these are reversible reactions, so depending on the amount of carbon dioxide, it can move towards the left or it can move towards the right. Why is this a big deal? Well, life exists in this water, and life is regulated by proteins, and proteins require a specific pH. So studies are showing that if we decrease the pH and make it more acidic, organisms are having a decrease in metabolism, and they can have a decrease in their immune response as well. Now, how much of a change in pH are we seeing? If we look at pre-industrial levels, the pH of the oceans was really basic, 8.25. Post-industrialization, it had changed to 8.14. Now, there are going to be regional differences you can see on this map right here. And you might say that's not much of a change in pH, 0.11, but remember this is a log scale. So that represents a 30% change in the pH. What's it going to look like in the future? Well, as we play those models out into the future, by 2100, it could be as low as 7.80. Now, this low pH is going to devastate ecosystems for a different reason. This last carbon compound of the 3 is carbonate. That combines with calcium to form calcium carbonate. That's what the shell is made up of. That's what the bulk of a coral reef is made up of. And as we change the pH, we can change the level of that carbonate. What determines the concentration of these 3? Well, it's going to be the temperature of the ocean water, the alkalinity, but also the pH. And so we can use a Jerome plot to figure out what's going to happen over time. These are log scales of the concentration of these 3 compounds. The green represents the amount of carbonic acid. The red line represents the amount of bicarbonate, and then the black line represents the amount of carbonate. Remember, that's important for shells. And so if we look at it at acidic levels, carbonic acid is going to dominate. At neutral levels, bicarbonate is going to dominate. And then at basic levels, those that we would find in the ocean, carbonate is going to dominate. But this blue area represents what's going to happen as we change the pH. And as we decrease the pH, you can see what's going on. The carbonate levels are going to drop off, and the bicarbonate levels are going to increase. That's because that free hydrogen is competing with the shellfish, really. The free hydrogen is competing with that calcium carbonate to form more bicarbonate. And so now shells can't make their shells. If we look at what could happen over time, this is a pteropod shell at 7.8 pH. It is literally going to dissolve. And so if we look at, for example, coral reefs, they're getting hit with a double whammy. We've got global warming. An increase in the temperature is going to cause them to bleach or kick out all of their algae. I'll talk about that in a different video. But this ocean acidification is going to take that carbonate, and so they can literally not build more of the coral reef. And so these 2 things work together. What's the good part of global warming and ocean acidification? If there is a silver lining, it's they both have the same cause. It's increases in the amount of carbon dioxide. If we can decrease the amount of carbon dioxide, we can cool off our planet, and we can also slow down this ocean acidification. I wanted to thank Rebecca Blake. She put this out as an idea of a video that I could make. I'm going to make a couple of videos based on this. If you would like to suggest a video, put it in the comments down below or send it to me on social media. That's ocean acidification, and I hope that was helpful.